So for what we're going to talk about today is we are going to talk about what it means for us to simplify radicals. So last class we defined radicals. We talked about this idea about how radicals and rational exponents were equivalent forms of each other. So just like in any system, when we begin to study it, think about what you guys did with fractions, right? The first thing you learn in fractions is you learn what it means to simplify fractions. So we're going to do the same thing with radicals. We're going to talk about what it means to simplify radicals, and then we're going to talk about what it means to multiply and divide, and then add and subtract radicals. So all those operations that we talked about with fractions, we're going to do the same thing with radicals. But we need to start off by talking about what it means to simplify radicals. So the first thing we have to be comfortable with is what it means for a radical to be in simplified form. Now, unlike fractions, if you remember something like fractions, if I had something like 14 over 20, and if we said to you, simplify this fraction completely, all you have to do are find two factors that the numerator and denominator share. We know we can rewrite 14 as 2 times 7. We can rewrite 20 as 2 times 10, and that's equivalent to saying 7/10. It's a little more complicated with radicals. So fractions, we just have one thing that we're looking for when we talk about simplifying them completely. In radicals, we have three things we're looking for when we talk about simplifying them completely. So we're going to talk about 1 and 2, and then we're going to spend a lot of time talking about number 3. Okay, so the first property. A radical is in simplified form if there are no fractions under the radical. So if we have a fraction under the radical, if we have something like this, right? Here's a radical with the fraction underneath it. This is not in simplified form. There's a problem. And what we're going to do is we're going to use various properties to help us write it as an equivalent fraction without a radical, to write it as an equivalent expression without a fraction under the radical. Okay, so 1, you can't have any fractions under the radical. 2, there are no radicals in the denominator. So what happens if we have a radical in the denominator? That means something like 5 divided by the square root of 7. That is not okay. That is not in simplified radical form. Or 6 divided by the cube root of 4a squared. Same thing, that is not in simplified form because there's radicals in the denominator. So something else we have to worry about is what happens or what do we do if we get a radical in the denominator, because we can't leave it that way. It's not in simplified form. Now, the third property, which is probably the more important property, I'm going to spend a nice amount of time talking about the third property, is no factors of the radicand can have a power greater than or equal to the index. So what does this mean? I'm going to spend a minute or two talking about this to make sure that you understand what it means. No factors of the radicand can have a power greater than or equal to the index. Okay, let's take a look at an example. Let's say I have something like the cube root of a to the 8th power, and let's compare that with the cube root of a squared. Okay, one of these you can simplify and the other one's already simplified. How do we tell the difference between the two? Well, let's do this. Let's compare. So we have the index of 3. We have an exponent of 8. So we have an index of 3. We have an exponent of 2. If your exponent is equal to the index or bigger, if you have an exponent that's greater than or equal to the index, you can simplify. This bit is simplifiable. If you have an exponent that's smaller than the index, you can't simplify. It's already in simplified form. Now we're going to talk about specifically what it means for us to simplify it, but understand that as I said before, this guy is not simplified. This guy is not simplified because the exponent is greater than the index. This guy is simplified because the exponent is smaller than the index. Okay, so the difference between the two of them is you compare the index and you compare the exponent. Once the exponent becomes either greater than or equal to the index, that means you can simplify it. Now let's understand something like this. If we have something like the cube root of 8, now we know that we could simplify the cube root of 8, and that's the same thing as saying 2, right? Because 2 times 2 times 2 gives you 8. Well, how does it work under this property? Well, remember that we can rewrite 8 as the cube root of 2 cubed. Now you see the exponent and index are the same, which means we can simplify that. That's why we say the cube root of 8 is equal to 2. That can be simplified. Now, if we compare it to something like the cube root of 4, well, that's the same thing as saying the cube root of 2 squared, right? And then notice here that the index and the exponent, when you compare them, the exponent is smaller than the index. So this can't be simplified. Okay, so again, comparing these guys, what you do really is you look at, if you have a factor, you look at what that factor looks like in its factored form. So 4 is the same thing as saying 2 times 2 or 2 squared, and 8 is the same thing as saying 2 cubed. And then you compare the exponent and the index. If the exponent is smaller than the index, you can't simplify it. If the exponent is greater than or equal to the index, you can simplify it. All right, so that's what this means. No factors of the radicand can have a power greater than or equal to the index, which means if you have a square root, you can't have anything that's raised to the second power or higher, 2, 3, 4, 5, 6, anything else. If you have a fourth root, you can't have anything that's raised to the fourth power or higher. You can simplify those terms. Okay, so we talked about this property before, which is the nth root of a over b is equal to the nth root of a divided by the nth root of b. Oh no, sorry, I think we talked about this property here, that we can break up products. We looked at it more in this way, that if you have, assuming they're all under the same index, that if you have a product, you can rewrite those products and break them up by each factor. Same thing with quotients. If you have a quotient, you can break up that quotient using each factor. So the nth root of a over b is the nth root of a divided by the nth root of b. The nth root of a times b is the nth root of a times the nth root of b. I'm just going to put a little bit more space, I'm sorry. And so what those properties are going to allow us to do is they're going to allow us really to simplify these guys as much as we possibly can. Okay. So here's one way that we can think about this. If we're dealing with the square root of 75, that means that we can't have any perfect square factors of 75. If we do have a perfect square or bigger factor of 75, then that means that we can simplify it further. So for these guys, what I like to do is I just like to think about all of the factors of 75, all of the factors of whatever the radicand is. So let's start off with 1 and 75. Taking my calculator out. 2 doesn't go into 75. 3 and 25. 4 doesn't go into 75. 5 goes into 75. 5 and 15. I don't think we have any other factors, so that's it. So what you do is you look at all of the unique factors of the radicand and you say to yourself, because we're dealing with the square root, do we have any perfect square factors in here? Remember, perfect square is a number times itself. 1 will always be a perfect square factor. 1's a perfect everything factor, but that's never going to help us to simplify a radicand. So what do we have over here? Well, we have the square root of 75 is the same thing as saying 3 times 25. Why 25? Because 25 is a perfect square. 25 is the same thing as saying 5 times 5. So what that means, excuse me, is that we can rewrite the square root of 75 as the square root of 25 times the square root of 3. So there was a factor of 75 that had an exponent of 2 or higher, right? And if you think about this, the reason why this works is because 25 is 5 squared. So we can call it 5 squared times 3, the square root of 5 squared times 3. And that means with this 2, there's a little hidden 2. That means we can simplify it, right? The square root of 5 squared, once you have the exponent and index, if they're the same, you can simplify. So that's why that property works above that we were talking about. But for here, in regards to simplifying it, the square root of 25, we already know is 5 because 5 times 5 is 25. Now the square root of 3, that's prime. It doesn't have any perfect square factors, so we just leave our answer like that. Let's take a look at the square root of 12. I'm going to do the same thing I did before. I'm going to break up 12 into factors. Now, look, this is something you don't have to do. If you're kind of comfortable writing these guys as factors in your head, that's absolutely fine, or like picking up the factors fairly quickly. But for those of you that are maybe a little bit slower than it, this is a good suggestion when you're simplifying these. So let's think of all the factors of 12, and then let's ask ourselves, because we're taking the square root, if there's any perfect square factors of it. So we have 1 and 12. We have 2 and 6. We have 3 and 4, and then we're done. We don't have any other factors of 12. Are any of these factors in here, factor pairs in here, any of these factor pairs equal to, or any of these factor pairs perfect squares? 1, again, will always be a perfect square. It's never going to help us simplify or reduce something. 2 is not a perfect square. There is no number times itself that would give you 2. Same thing with 6. It's not a perfect square. There is no number times itself that would give you 6. 3 is not a perfect square. 4 is, right? We know 4 is a perfect square because we can rewrite 4 as 2 squared. So when we break up the square root of 12, we can call that the square root of 4 times the square root of 3. It's equal. That's what the property above tells us, that if we can break up products, assuming that we have the same index. We know the square root of 4 is 2. Square root of 3 is the square root of 3. So the answer to B is 2 times the square root of 3. Okay, let's take a look at a bunch more of these guys. Let's take a look at, oh, here's some other good examples over here. Let's take a look at the cube root of 40. What does it mean for us to simplify the cube root of 40? Now our index has changed. So now instead of looking for perfect squares, we're looking for perfect cubes. So I'm going to list all of the factors of 40, and then I'm going to look for any factors that are perfect cubes or higher. So what do we have? Well, we have 1 and 40, 2 and 20, 4 and 10, 5 and 8, 6 and 7, nothing else. These are all the factor pairs of 40. So we're looking for perfect cubes. Are any one of these numbers equal to a perfect cube? Remember, perfect cubes are if you multiply a number by itself 3 times. No, no. 1 is again, but that's never helpful. So I'm just going to call it a no. 2 and 20, neither one of these are perfect cubes. There is no number if you multiply it by itself 3 times, it will give us either 2 or 20. What about 4 and 10? Are either one of these perfect cubes? Well, there is no number if we multiply it by itself 3 times, that will give us 4. There is no number if we multiply it by itself 3 times, that will give us 10. What about 40? Oh, excuse me, what about 5 and 8? Well, 5 is not a perfect cube. 8 is. Right? 8 is a perfect cube because 2 times 2 times 2, or 3 factors of 2 will give us 8. So this means we can break up the cube root of 40, and that's the same thing as saying the cube root of 8 times 5. Okay, so remember, we can break up products assuming the index is the same. So this is equivalent to saying the cube root of 8 times the cube root of 5. Like we said, we know the cube root of 8 is 2. The cube root of 5, there's nothing we can do with that. We're just going to keep that as the cube root of 5. 5 doesn't have any perfect cube factors, and this is what we're left with. Other examples, I would like for you guys now to see if you can pause D and see what you can do in regards to simplifying the square root of 40. So for the square root of 40, now notice that the radicand was the same in both these guys, right? We used 40. And then I used 40 here. But what is different is the index. So here, this is a cube root, so we're looking for perfect cubes. This guy is a square root. So here we're looking for perfect squares. So we can use the same factors. And take a look at these guys. Are any of these factors perfect squares? Yes, but again, it's never helpful. 2 is not a perfect square, neither is 20. 4 is a perfect square, right? 4 is the same thing as saying 2 times 2, which means I can break this apart, and I can call this the square root of 4 times the square root of 10. That this value always has to be equal to that initial radicand that we started with. Okay, so let's simplify the square root of 4 times the square root of 10. Well, we know the square root of 4 is 2. We can't simplify the square root of 10. 10 only has 2 factors besides for 1 in itself, and that's 2 and 5. Neither one of them are perfect squares, so we're done. The answer to this is 2 times the square root of 10. Okay, so let's try a few more examples. And again, you're going to see the index is going to change for a lot of these because I really want you to get used to looking for those perfect nth values, whatever they are. So here we have we're looking for a perfect fourth exponent. I don't even know how to say that. Quartic, maybe? Perfect quartic exponent. So this means we're looking for a number if you multiply it by itself 4 times. That's a factor of 32. So I'm going to start by listing, we're looking to see if we can simplify it. It's possible they're not simplifiable. But let's list the factors of 32. So I'm going to start from the beginning. 1 and 32. We have 2 and 16. 4 goes into 32 8 times. I believe we're done. 5, 6, 7 doesn't go in and we're finished. Are any one of these perfect fourth exponents? 32 isn't. There is no number if you multiply it by itself 4 times that will give you 32. 2 is not. There is no number if you multiply it by itself 4 times that will give you 2. Think about 16. Jackpot, ding, ding, ding. 16 is the same thing as saying 2 times 2 times 2 times 2, right? 16 are 4 factors of 2. So we can rewrite the 4th root of 32. Oh, that's a giant 4, sorry. Let me make sure that your index is in the upper left-hand corner of the radicand there. So we have the 4th root of 32. That's the same thing as saying the 4th root of 16 times the 4th root of 2. Now, I always just like to put the perfect values over here in the front because it just kind of pops out there, but the order is unimportant. I could have just as well called this the 4th root of 2 times the 4th root of 16. All right, what is the 4th root of 16? Well, the 4th root of 16 is 2, and, right, because 2 to the 4th power is 16. And this 4th root of 2, there's nothing we can do to simplify it, so the answer to this guy is just 2 times the 4th root of 2. Take a look at F. We have the cube root of 250. Let's simplify the cube root of 250 as much as we possibly can. Well, here we're looking for perfect cube factors of 250. So again, I'm going to start listing some factors of 250. 1 and 250, 2 and 125. 3 doesn't go into it, 4 goes into 250. 4 does not go into it, 5 goes into 250. 5 and 50. 6 doesn't go, 7, 8, 9, 10 goes into it, 10 and 25. Let's see what else. 5, 2, 5, 5, that's it. This is it. Are any one of these perfect cubes? No, yes, but it doesn't matter. No, no, yes, 125 is, right? Because 125 is the same thing as saying 5 times 5 times 5. And if it helps, you could maybe put off on the side a bunch of factors that are perfect squares, a bunch of factors that are perfect cubes, a bunch of factors that are perfect fourths. Sometimes that helps you really recognize what they are fairly quickly. So the cube of 250 is the same thing as saying the cube of 125 times the cube of 2. The cube root of 2. The cube root of 125 times the cube root of 2, and 125 times 2 gives us 250. And we know we can simplify this. The cube root of 125 is 5. So we end up with 5 times the cube root of 2. Okay, square root of 72. Let's talk about the square root of 72. Well, we're looking for perfect square factors. Now, the reason I gave you this one is because I want you to see that sometimes some of these factors will have a lot of perfect square factors or a lot of perfect cube factors. 72 is one of them, and I want to show you how to kind of get out of that situation. So 72 is 1 and 72. It's 2 and 36. It's 3 and 24. It's 4 and 18. It's 6 and 12. It's 9. Oh, sorry. It's 8 and 9. Lots of factors of 72. Now, in regards to perfect square factors, I challenge you now to find 3 of them. They have 3 perfect square factors. You see the 3 perfect square factors. Well, 9's a perfect square, so we could break it up into 9 and 8. 4 is a perfect square, so we could break it up into 4 and 18. 36 is a perfect square, so we could break it up into 36 and 2. Now, the idea behind this one is if you have a number with lots of perfect factors, with square, cube, whatever it is that you're looking for, you really want to choose the biggest factor. Now, I'll show you why it's okay to choose factors that are smaller, but let's start off with choosing the biggest factor. So you say, okay, well, 36 is the biggest factor, so I'm going to break this up into the square root of 36 times the square root of 2. And that's the same thing as saying 6 times the square root of 2. But let's say I didn't quite recognize that that was the biggest perfect square factor. So let's say instead of using 36 and 2, let's say I used 4 and 18. If we were to break up the square root of 72 into the square root of 4 times the square root of 18, it would look like this, right? We know the square root of 4 is 2. But now think about the square root of 18. I want you guys to think about factors of 18. 18 has factors 1 and 18. 18 has factors 2 and 9. 18 has factors 3 and 6. So 18 has a perfect square factor in it, right? 9 is a perfect square, so we can break that down even further. We would have 2 times the square root of 9 times the square root of 2. And watch what happens. It's really neat. The square root of 9 is 3. 2 times 3 is 6. 6 square root of 2. Look at that. We get the same thing. You just have to do it in extra steps. So that is, you'll be left with a radicand that's still simplifiable if you don't choose the biggest perfect square factor of it. Either way, though, you get the same answer, right? It just makes for the possibility of making more mistakes if you don't choose the biggest perfect square factor. Okay, square root of 30. Pause right here. See what you guys can do with the square root of 30. See if you can simplify that completely. Okay, how did you do with the square root of 30? Well, let's list all the factors of 30. We're looking for any perfect square factors of 30 here. 30 has, what does 30 have? 1 and 30, 2 and 15, 3 and 10, and we're done. Isn't that mean? Let's see. 1 and 30. 1's a perfect square, but nobody cares about that, right? 2 and 15. 2 is not a perfect square. There is no number times itself that gives you 2. 15 is not a perfect square. There is no number times itself that gives you 15. 3 and 10. There is no number if you multiply it by itself that will give you 3. Same thing with 10. There is no number if you multiply it by itself that will give you 10. So guess what? Square root of 30 is already simplified. It doesn't have any perfect square factors. So literally we just leave it alone. We're like, oh, done. It's the same thing, you know, if in fraction terms, if I said to you simplify 3/7 and you would say, well, 3 and 7 don't share any factors, we're done. We don't have to do anything to it. Same thing here. So the square root of 30 cannot be simplified. It doesn't have any perfect square factors. Now let's take a look at one more, and then you see what's coming up, right? Is that we're going to start adding some variables and exponents into this too. And then we're going to talk about the other properties for simplifying radicals. But think about the square root of 8. Eight's going to show up a lot. The square root of 8, that's equivalent to 4 is a perfect square factor of it. The square root of 4 times the square root of 2. And so we can rewrite that as 2 radical 2. So that's the square root of 8 simplified completely. Okay, what happens now? Let's take a look at this. What happens now if I have bases and exponents in here as well? So if we're dealing with something like the cube root of 729, a to the 9th, b to the 7th, this is equivalent to saying the cube root of 729 times the cube root of a to the 9th times the cube root of b to the 7th. Let's see what we can do in terms of simplifying these. Let's do 729 first. So does 729 have any perfect cube factors? Well, guess what? 729 is a perfect cube. How do you know? Well, 729 is the same thing as saying 9 times 9 times 9. Would have just erased all of this. I was not happy. So this guy is a perfect cube, and we're just going to call this 9. Now let's take a look here at the cube root of a to the 9th. And if you guys remember last class, we talked about this idea that anytime that you have an exponent and an index, you can just ask yourself, how many times does that exponent, or how many times does that index go into that exponent, or what is the exponent divided by the index? So a to the 9th, the cube root of a to the 9th, well, 9 divided by 3 is 3. So that's the same thing as saying a cubed. And now we're going to get to some examples with what happens where it's divisible, but we have a remainder. So let's take a look at the cube root of b to the 7th. Well, the cube root of b to the 7th, that's the same thing as saying b to the 7/3 power, right? Just like the cube root of a to the 9th is the same thing as saying a to the 9/3 power. And we know 9 divided by 3 is 3. Well, the cube root of b to the 7th is b to the 7/3 power. Those are going to be exponent divided by index. So what does that mean? Well, this is an improper fraction. If we were to rewrite this improper fraction as a mixed number, we know 3 goes into 7 2 times with a remainder of 1. So we get b to the 2 1/3 power, which means the following. I have 2 complete factors of b, and I have a third left over. So b to the 1/3 power is the same thing as saying, remember, exponent index, this is exponent and this is index, is the same thing as saying the cube root of b to the 1st power. So the idea is for these guys, whatever whole number you get, whatever the quotient is that you get when you divide these two, so 7 divided by 3 is 2, that's going to be on the outside of the radical. Whatever your remainder is, that hangs around on the inside of the radical. And we knew we could simplify both of these, right? Because in both of these cases, the exponent was larger than the index. If the exponent's smaller than the index, you can't simplify it. If the exponent's bigger than the index, then you can. Okay, so let's do 2 more like that. I want to make sure that you guys understand exactly what it is that we're looking for here. Now I'm going to break this up into 3 different parts. Sorry, 4 different parts. Oh, we have 4 different factors there that we're dealing with. So we have the 4th root of 16, k to the 21st, y to the 42nd, z cubed. Let's break this up into 4 different factors. So this is the same thing as saying the 4th root of 16 times the 4th root of x to the 21st times the 4th root of y to the 42nd times the 4th root of z cubed. It's a lot of writing. It's okay. So let's look at this first. The 4th root of 16. Does 16 have any perfect 4th factors? Well, it turns out, just like the example above, that 16 is a perfect 4th, right? 16 is the same thing as saying 2 to the 4th. So the 4th root of 16 is 2. Done with that guy. Now let's take a look at the 4th root of x to the 21st power. So we know that we can simplify this because the exponent's larger than the index. We need to figure out how many times 4 goes into 21, or what's 21 divided by 4. Well, we know we can get 5 complete groups of 4 out of it. And then what are we left with? So this is on the outside. What are we left with? What are we going to be left with on the inside of the radical? Sorry, I'm just trying to space this guy out appropriately. Well, 5 groups, remember this is the remainder that we're left with here. So 21 divided by 4 is 5 with a remainder of 1. So we're going to put 1x left over in there. Same thing, let's take a look, and this is the 4th root, sorry. Let's take a look at the 4th root of y to the 42nd power. Well, how many times does 4 go into 42, or what's 42 divided by 4? Well, we know that we can get 10 groups of 4 out of there. 42 divided by 4 is 10. And we have a remainder, 4 times 10 is 40. 42 minus 40 is 2. We have a remainder of 2. So again, quotient on the outside, remainder on the inside. And then let's take a look at the last term, the 4th root of z cubed. Exponent's smaller than the index, so we can't simplify it. So we're just going to leave that z cubed on the inside of the radical like that. Okay, try L on your own. See what you can do in terms of simplifying part L all by yourself. Okay, welcome back. Let's take a look at L. We have the cube root, and I'm going to break this up because we have 4 different factors here. We have 16, we have x squared, we have y to the 15th, and z to the 19th. So I'm going to break this up into 4 different terms. Cube root of 16, cube root of x squared, cube root of y to the 15th, cube root of z to the 19th. Let's start off with the cube root of 16. Now 16 is not a perfect cube, but what we need to do is we need to find factors of 16 that could be a perfect cube. So we can rewrite 16 as 1 and 16, 2 and 8, 4 and 4. Any of these guys perfect cubes? 8. So I can redo it like this. The cube root of 16 is the same thing as saying the cube root of 8 times the cube root of 2. So we have one factor, the cube root of 8 is 2. We have one factor of 2 on the outside. And then one factor of 2 is going to be left on the inside of the radical. I'm going to do this. There's going to be a bunch of stuff on the outside, a bunch of stuff on the inside. Now let's take a look, crossing it out because we're done. We have 3 little other terms to look at. Let's take a look at the cube root of x squared. Again, here, notice that my exponent is smaller than my index, so I can't simplify that. So I'm going to leave it like this. For the cube root of y to the 15th power, 3 goes into 15, or 15 divided by 3 is 5. And there's no remainder. So we're not going to have any radicals. We're not going to have any factors of y left over on the inside of the radical. And then the last term, the cube root of z to the 19th, how many times does 3 go into 19? Well, it goes in 6 times. So we have z to the 6th. And remember, we have a remainder of 3 times 6 is 18. 19 minus 18, we have a remainder of 1. So z to the 1st. That's what this guy looks like simplified completely. So we talked a lot about that property over here in terms of what it means if we have factors of the radicand that have exponents that are greater than or equal to the exponent, greater than or equal to the index. And we talked about how to simplify it. But we still need to talk about these first 2. So that is, if you see a fraction under a radical, or if you see a radical in the denominator, they're not simplified completely. So there's some little algebraic tricks that we have to pull out of our hat, of our bag of tricks, to be able to simplify them completely. And one trick that we're going to use is that trick that I talked about above, is that the nth root of a over b is the same thing as saying the nth root of a divided by the nth root of b. So you can break up quotients. So let's do that. Notice here that I have a fraction under the radical, and that's not okay. So I'm going to break this up. This is equivalent to saying the square root of 25 divided by the square root of 4. Now, okay, so what we did is we broke it up, but now notice I have a radical in the denominator, and I also have perfect square factors in both. So what does that mean? Well, we have to try to simplify them further. Let's take a look in the denominator first. Square root of 4, can we simplify it? We certainly can. That's the same thing as saying 2. Square root of 25, can we simplify that? We certainly can. That's the same thing as saying 5. Now I've simplified it completely. I got rid of all radicals. I got rid of all fractions under the radical. I got rid of all radicals in the denominator. And I don't have any perfect square factors left in my square roots because there are no square roots left. It turned out that both of these guys were perfect square factors anyway. So this is equivalent to saying 5/2, but you know what happens. You know it's going to get more interesting. It's going to get a little more complicated. So let's take a look at some other examples. Let's take a look at the cube root of 24 over 27. Well, that's the same thing as saying this. Right? Now, again, same thing we did before. Once you break up a quotient like this, then you have to say to yourself, okay, well, I'm still breaking some laws here because I have a radical in the denominator. But it turns out the cube root of 27 is a perfect cube, right? The cube root of 27 is the same thing as saying 3 because 3 to the 3rd power is 27. So that's simplified. Now we have to go upstairs and take a look at the cube root of 24. Well, what law could we possibly be breaking here? Well, that third rule, we could possibly have a perfect cube factor of 24. So we have to check and make sure that we don't, so that it's simplified completely. So let's talk about 24. Well, factors of 24. 1 and 24, 2 and 12, 3 and 8, 4 and 6. Are any one of these perfect cubes, right? We had that index of a 3, so we're looking for perfect cubes of it. You're right, 8. So we actually can simplify the cube root of 24. We can call that the cube root of 8 times the cube root of 3. And we know the cube root of 8 is 2. So this guy's 2. This we can't simplify. And this guy's 3. So here's an example that kind of broke all 3 of those rules. We had a perfect cube factor in a cube root. We had a fraction underneath the radical, and at a certain point, we had a radical in the denominator. So we took care of all 3 of those rules in terms of simplifying this one completely. Okay, let's take a look at part C. The square root of 4/7. Exactly the same thing we did before, we're going to do here. So we're going to call that the square root of 4/7. That's the same thing as saying the square root of 4 over the square root of 7. Right? And then we're going to say, well, can we simplify this in any way because I have a radical in the denominator? No, right? 7's not a perfect square. There's nothing we can do with that. 7 doesn't have any factors of it that are perfect squares. 7's prime. The only factors of it are 1 in itself. Notice our numerator, you can simplify that. I mean, that's going to help us a little bit, but we're still breaking that law of having a radical in the denominator. So what do? Now I'm going to take you back to something we've been spending a decent amount of time talking about, and that is finding equivalent fractions. Now remember that anytime you're looking for equivalent fractions, as long as you multiply the numerator and denominator by the same number, you'll get equivalent fractions, as long as it's not 0. So what we need to do, because we're dealing with the square root, is we have to force the denominator to become a perfect square somehow, because if you have a perfect square, you can take it out of the square root. So the trick is this. Anytime you have a square root in the denominator that can't be simplified, multiply the numerator and denominator by whatever that factor is. So I want you guys to see what's going to happen here. Numerator, I have 2 times the square root of 7. Denominator, the square root of 7 times the square root of 7 is the square root of 49. Now, why is this helpful? Look at the denominator. 7 times 7, we're forcing the denominator to be a perfect square, right? If you multiply anything by itself, it's going to be a perfect square. So what that means is I can get rid of that radical in the denominator because it's a perfect square, and the square root of 49 is 7. Let's take a look at the square root of 3/5. Again, I'm going to do exactly the same thing I did before, and I'm just going to rewrite it like this. Can I simplify this? Nope, nothing I can do with that. Can I simplify this? Same thing, nothing I can do with that. But so none of these guys have perfect square factors in them. We can't simplify them completely, but we're still breaking that law where we have a radical in the denominator. So how do we get rid of the radical in the denominator? What's the trick? Well, remember, we're going to multiply the numerator and denominator by itself. We're going to multiply the numerator and denominator by whatever the denominator is. We have to multiply them both by the same term because we're finding equivalent fractions. And specifically, we're multiplying the denominator by itself because we're forcing it to be a perfect square. Why are we forcing it to be a perfect square? Because we have to take it out of the square root. Numerator, now I have the square root of 15. Denominator, the square root of 25 is 5. So that's this guy simplified completely, the square root of 15 over 5. Okay, let's take a look at a few more examples of these guys. Let's take a look at the cube root of 5 over 3. We can do this. Right, same thing we did before. Now what? Well, I can't simplify the cube root of 5. I can't simplify the cube root of 3. So can I just do what I did when I had a square root in the denominator? That is, would it make sense for me to multiply the numerator and denominator by whatever factors in the denominator? Let's check it out and see if that helps. When we get the cube root of 15 over the cube root of 9, can we take the cube root of 9? No, it's not a perfect cube. So that only works if you have a square root in the denominator. If you have any other index in the denominator, then it requires a little bit more thought. So here's what we need to do. When we talk about the denominator now, we need to force the denominator now to be a perfect cube, not a perfect square, to be a perfect cube. And to be a perfect cube of something, that means you need 3 factors of it. Perfect square, you need 2. That's why it's okay to just multiply it by itself. A perfect cube, you need 3 factors of it. So what you do is you say to yourself, okay, well, over here, I have 1 factor of 3. I need 2 more factors of 3. And think about what 2 factors of 3 look like. 3 to the 2nd power is the same thing as saying 9. And that will guarantee, so here's 1, 2, 3 factors of 3. Whatever you multiply the denominator by, you have to multiply the numerator by the same thing. That will now force our denominator to be a perfect cube factor. So in the numerator, we have 5 times 9, which is 45. In the denominator, we have the cube root of 3 times 9, which is the cube root of 27. We can simplify the cube root of 27, right? Because we forced it to be that way. The cube root of 27 is the same thing as saying 3. So we got rid of the radical in the denominator. And the cube root of 45, well, 45 doesn't have any perfect cube factors, so we would just leave the answer alone like that. So the answer to this one is the cube root of 45 divided by 3. We got rid of all fractions under the radical. We got rid of all radicals in the denominator, and we didn't have any perfect cube factors of the radicand to worry about. Okay, let's take a look at 3 more examples. The cube root of 3 divided by the cube root of 2a. Again, here, remember that I'm not looking for a square root, I'm looking for a cube root. So, and I'm also throwing a denominator into the mix. I'm just upping the ante a tiny bit, making it a little bit more interesting than I was looking at before. So we need to somehow force 2 to be a perfect cube, and we have to force a to be a perfect cube. So if you have 1 factor of 2, you need 2 more factors of 2. That will give you a total of 3 factors of 2 to give you a perfect cube. So here's 1 factor of 2, 2 more factors of 2, or 2 times 2 is 4. So we're going to multiply the numerator and denominator, first of all, by 4. And now let's take a look at a. Same thing, we need to guarantee that we have 3 factors of a here. And here I only have 1 factor of a. So I need to introduce 2 more factors of a to give us a perfect cube. So we're going to multiply the numerator and denominator by 4a squared. Now let's see what we get. In the numerator, I get the cube root of 12a squared. In the denominator, I get the cube root of 8a cubed. How does that help? Well, look at our denominator. The cube root of 8 is 2. The cube root of a cubed is a. Our numerator, the cube root of 12a squared, is just the cube root of 12a squared. We only have 2 factors of a, so we can't simplify that, right? Because the exponent's smaller than the index. And if you think about all the factors of 12, none of these guys are perfect cubes. So we're good. That's that guy simplified completely. Okay, 2 more examples. Let's take a look at just the just the square root of 3 over 2a. Well, again, I'm going to start off and say, well, the square root of 3 over 2a is the same thing as saying the square root of 3 over the square root of 2a. Now notice it's a square root, so that means it's a lot less thought that's involved here. You can just multiply the numerator and denominator by itself. So in my numerator, I have 3 times 2a, which is 6a. In my denominator, I have 2a times 2a, which is 4a squared. And remember, this works for square roots, but no other root, no other index, if you multiply it by itself. because if you multiply something by yourself, you get a perfect square and you can take that out of a square root. 4 times a squared is 2a. And left on the inside of my radical is the square root of 6a. I can't take the a out because remember there's a hidden 2 here and a hidden 1 here. And there's 1 is smaller than 2. And 6 does not have any perfect square factors. So we leave the answer alone like this. It's the same thing as saying the square root of 6 times a to the first. Okay, last one. Get excited. We have one more example. Let's take a look at h. Okay, so now we have to multiply the numerator and denominator by the 4th root of something. The indexes have to be the same. And that means if it's the 4th root of something, we need 4 factors of it. All right, so let's start off with the b. We have 3 factors of b. To get a total of 4 factors of b, we have to introduce one more b. We have 2 factors of a. To get a total of 4 factors of a, we have to introduce 2 more a's. We have 1 factor of 2. To get a total of 4 factors of 2, we have to introduce 3 more factors of 2. 2 times 2 times 2 is 8. So in our numerator, in our denominator, so we get our numerator, 7 times 8 is 56. And then we have a squared b. In our denominator, 2 times 8 is 16. A squared times a squared is a to the 4th. B cubed times b to the 1st is b to the 4th. Remember, our ultimate goal is to get rid of any radicals in the denominator, so we shouldn't be left with any radicals at all in the denominator. That's the whole purpose behind doing this in regards to simplifying it. We know the 4th root of 16 is 2. We know the 4th root of a to the 4th is a. We know the 4th root of b to the 4th is b. Simplifying the numerator completely, well, there's only 1 factor of b here. And 1 is less than 4, so we can't take that out. There's only 2 factors of a, and 2 is less than 4, so we can't simplify that. And the 4th root of 56, 56 does not have any perfect 4th factors in it. So this is our answer, simplified completely. Okay, so we talked about how to simplify radicals. Simplifying radicals was fine. We talked about how radicals are the same as rational exponents. Stay tuned because next class we're going to talk about, in the upcoming classes, we're going to talk about what it means for us to add, subtract, and multiply and divide radicals. Now I'm going to tell you something radical to do. Here's a radical idea. Do your homework. See you next class.